Section 6.2, multiplying and dividing radical expressions, which really, that's our objective. We want to be able to multiply and divide radical expressions effectively, but we also have to be able to simplify. Everything that we do in Algebra 2, whatever we get for an answer, we have to recognize when we can take it a little bit further, make it a little bit easier to use, and simplify it. So that's a big piece. Multiply and divide radical expressions, as I mentioned, probably just multiply today. I don't expect to go into division. So our getting ready gives us an example of a visual way to think through what this is going to do for us. It says you can cut 36 squares. So over here we've got this 36 little squares square into 4 nines. Sure you could. 4 squares, 9 in each one of them. Or you could use 9 fours to make them squares. That's what's important. If we're going to talk about square roots, we need things that are perfect squares. So we notice we're getting perfect square answers for these. This is 3 by 3, which is 9, which is a perfect square. This is 2 by 2, which is 4, which is a perfect square. And it says, what other n squares could you cut into sets of smaller squares in 2 ways? Is there a square you can cut into smaller squares in 3 ways, and explain the reason? Well, to do that, we kind of have to see, why is this working? You know, for 36, why does this work? I'm going to take you back to some elementary math. That elementary math is to make a factor tree. Factor tree. So you look at 36 and you say to yourself, I know I can divide it by 2. So 2 will go in there 18 times. Oh wait, it's still divide 18 by 2. I'll do that. Keep bringing this 2, but now it's going to be 2 times 9. Oh wait, 9 is divisible by 3. So 2, 2, 3, and 3. And how you know you're done is if you get down to an integer that is not divisible by anything but 1 and itself. So I look at this and I see this looks kind of unique. Because we had 2 2s and we had 2 3s. Wait a minute, that makes sense. Because this would be 4 if you multiplied them together, and this would be 9. Those are perfect squares. That's the reason that it worked. So if we wanted to come up with another one, whether or not we were talking about 2 or 3 different ways, we'd realize, well, all I need to do is start at the bottom and work my way up. Come up with some other numbers that would do this. Maybe a 3, and a 3, and a 5, and a 5. That would do it, because we'd have 9, and we'd have 25, and work your way back up to the problem by just saying 3 times 3 is 9, 5 times 5 is 25, and take 9 times 25. If we wanted it to be able to split 3 ways, we could add 7 times 7 over there again. So then we would have 3 situations where we could split that into perfect squares. So factor trees are an option, but factor trees also take some time, and sometimes it doesn't have to be that difficult. And that's the reason we have that power chart, is because if we want to break this into perfect squares, we want to be able to say, all right, if we've got the square root of 36, yes, we know the square root of 36 is 6. So we can get those 2 perfect squares that we need. But if we have one that doesn't work out perfect, 72 is not a perfect square. We want to be able to think through simplifying that just the way you did before with square roots. And you said, hey, wait a minute, 36 goes into that twice. So this will be 6 square roots of 2. But how we're going to do it with cube roots and 4th roots and 5th roots. And that's why that power chart is so important, because you can start to look those up. Now, if you love making factor trees, go for it. Factor trees will work for this. They definitely will. But like I told you before, your memory is going to retain more if you're looking up that information on that power chart and using that instead. So, do you remember all your perfect squares? 1 squared is? 2 squared?
4.
3 squared? 4 squared?
16.
5 squared? 6 squared? 7 squared? 8 squared? 9 squared? 10 squared? 11 squared? 12 squared? 13 squared.
169.
14 squared. Yeah, see, I've got a little quieter that time. It's always easy for me to remember that it's going to be 196 because look what you do. You just transpose these two numbers back. 15 squared. That's probably about as far as we need to go. I know some of you memorize those all the way up to 20, but that's generally about as far as we're going to need. Because our focus in this section is not necessarily on the square roots. I mean, you've done that before. You did that in exponential. So now it's, okay, now I have to think in terms of perfect cubes and perfect fourths. That's going to be a little tougher to start with. It won't be horrible. It'll be a little tougher. So we've got our perfect squares. And what we need to realize is what we did with perfect squares when we were simplifying is the same thing we're going to do with our perfect cubes and our perfect fourths. We're not learning new math here. But I have talked to you before about how when we're breaking these up, we can do that because if you multiply two square roots together, you get a square root. If you multiply two cube roots together, you get a cube root. What you cannot do is try to take a square root times a cube root and simplify. Can't happen. They have to have the same index. So just as if we wanted to use exponents, powers of exponents to do this, if we have 2 squared times 3 squared, hopefully we would notice, wait a minute, they both have a 2 for a power. I wonder, if I keep that 2 for a power, can I just do the 2 times 3? Well, of course you can. Because remember, if there's multiplication in here, we distribute the power. It works. So we have to think about that index as the power when we're working with these and make sure that that index is going to be the same. So you can simplify a radical expression when the exponent of one factor of the radicand is a multiple of the radical's index. And you can simplify the product of powers that have the same exponent. Similarly, you can simplify the product of radicals that have the same index. Index is important. So, property. Combining radical expressions by products, by multiplying. If we have the nth root of A and the nth root of B, and they're all real numbers, when we take the nth root of A times the nth root of B, because the index is the same, we're just going to write nth root over the whole thing and multiply the two numbers together. So instead of pulling it apart, they're putting it together here. But it works forwards and backwards. So this is what allows us, if we recognize a perfect square, a perfect third, a perfect fourth, that we can pull it back apart. Because it works in both directions. And that's a lot of what we're going to do today. We're going to put things together, but then we'll pull them apart if we can simplify. So down here, can we simplify the product of the radical expressions? They're not really asking us to yet. They're just asking us, yes or no, can we do it, why or why not? Take a look at A. Can we put those two together? Oh, one's a cube root and one's a square root. No. Different index. Can't do it. Index has to be the same. Take a look at B. Can we do that one? Yes. In fact, it's really hard not to. We do cubed root of, and we would go ahead and do the multiplication and say negative 4 times 2. That's negative 8. Oh, we've done harder than that. That answers negative. So this is yes because the index is the same. So just like we work with those like powers, we're going to work with like indices when we go through these. Can we simplify the product of the radical expressions and explain? Go ahead and write down your answers for A and B. Yes or no, why or why not. We're going to build up your confidence in your answer with a chicken wing elbow partner. Chicken wing elbow partners are if you were chicken and you were flapping your wings somebody's close enough that maybe you could get, no, we don't have to test that close together. But it basically means somebody in front of you, behind you, off to one of your sides. So take your paper, grab a chicken wing elbow partner, see what they got, what you got. Now that you're confident in your answer, what'd you put for A? Why? I have the same index. What'd you put for B?
Yeah.
That's a yes?
Yeah.
They have the same index. So then the next part of this is going to be, well, what would it be? I mean, if you know you can do it, what would you get? Write it down. Check with chicken wing elbow partner. Anything you can do with that? Well, if we could simplify it, on our power chart, underneath fifth power, there would have to be a perfect fifth power that would divide into 10 evenly. Grab your power chart. Do you have any perfect fifth powers that are going to divide into 10 nicely? Not a one. That's done. That's as simple as it gets. But that's the next step in this is, hey, if you can get the answer, find it, now simplify it. You know, find what it should be. So that's next. That's where we're going. We have to reduce a radical as much as possible to have that in simplest form. And just like when we were talking about perfect squares and simplifying, we had to take out any perfect squares that were factors of our radicand. Well, now we're going to have to take out any perfect cubes, any perfect fourths, any perfect fifth roots that we see. So the square root of 24, biggest perfect square that goes into it nicely. 4, that's it. It's not very big. And it goes into it 6 times. So notice how we're using that property backwards now. We're saying, yeah, it's already been multiplied together, but let's split this up to simplify it. And that would give us 2 square roots of 6. Now we don't do the plus or minus piece because they already had the square root there for us. We're supposed to know, hey, this means principal root. Cube root of 24. Huh. Bar chart handy. Do we have any perfect cubes that would go into this? What is it? 8. Cube root of 8. Cube root of 8 times what gives you 24? 3. Well, the cube root of 8 is 2. Got any more perfect cubes that'll divide nicely into 3? Other than 1, because 1 doesn't do anything for us. We're done. We took out that perfect cube that we could take out of this. And that's the simplest form. So down south we have, what is the simplest form of has a variable in it? Well, take it in steps. What we just did was said, all right, we can do this. We know how to do that. That's cool. All right, got that down. Well, yesterday, we did that with the variables. Cube root of 54. Check your list. Perfect cubes that would divide nicely into 54. 27, how many times? Twice. Cube root of x to the 5th. Well, 3 doesn't go into that perfectly, so we'll have a cubed root of x to the 3rd, and then we'll have a cubed root of x squared. Well, like yesterday about how they're not always going to be perfect. So, cubed root of 27, what is that? 3. Cube root of 2, something very nasty. In your calculator, nasty decimal. Now stay clear of that. Cube root of x to the third, well, that's x. Cube root of x squared, you can't do any more with that. Remember yesterday I said the ugly remainder stuff has to stay under the ugly radical. Yeah, so we've got cube root of x to the fifth. 3 goes into 5 once, nicely, but it's going to have an ugly remainder of 2. So now here's what we do. Just like in the real world, you put the pretty stuff out front and you put all the ugly stuff in the back. So the 3 and the x are pretty, and all the ugly stuff gets joined together back in the back. One last step. This is a variable. We have to figure out if this needs an absolute value bar set on this x here. Tell a chicken wing elbow partner whether or not you need absolute value bars on this little x right here. Make them tell you why. Wrong. I eavesdrop up here when you have chicken wing elbow partners. I heard because it has an odd index. Absolutely. It's an odd index. We don't need absolute value bars when we have an odd index. But notice how we're putting pieces together. We're already doing, all right, let's make this number in simplest form. Yesterday we already did, hey, let's get this radical in shape. Today it's, let's put all that together and don't forget to think absolute value. So different steps as we go through this. All right, here's the got it. 2. 43210 me on how you feel right now about these pieces together. Not bad numbers. Try this one on your own. See what you do. So you can see what you can. We've got chicken wing and new level partner. Because there are some people that don't have the right thing down. Some of them got hung up on the cube root of 128 and couldn't find a perfect cube that went into it. So check in with a different chicken wing elbow partner. Here was where some people got hung up, right there, trying to find that cube root. So what do you do if you get hung up? Go back to factor trees. That's what you do. Take a second and you say, okay, let's say 128. I know 2 goes into that 64 times. Now hopefully you stop there and you check your factor tree and go 64. But let's say you didn't. Let's say you didn't notice that. So you keep going and you say, all right, 2 and 32. Well, I'll go with 2 again. 2 and 16. 2 again. 2 and 8. 2, 2, 2, 2, 2, 2, 2. What does that help you do? Well, it helps you see you got a ton of 2's. So pretty obviously we want to group those in groups of 3 to figure out what we have going on. So we've got 1, 2, 3, 4, 5, 6, 7. Oops, too big enough for you to see it. So there's got to be a 2 to the 3rd in there. In fact, there has to be 2 of them, because it would be 2 to the 3rd times 2 to the 3rd times 2 to the 1st. 2 to the 3rd is 8. 8 times 8 is 64. So 64 should work in it. You go to your power chart and you see 64. Now that's the long way. Now, obviously, you could use your power chart and just work your way back up and find one that goes into it nicely. But if you can't find it, factor trees, they work. So, cube root of 64, what is it? Cube root of 2? Nasty. Cube root of x cubed? X. Cube root of x cubed? X. Cube root of x to the 1st? Nasty. Beautiful stuff out front. 4x squared. Nasty stuff in the back. Oh, did I write the wrong? Oh, thank you. I was just thinking. Absolute value bars. We need that on this one. Why not? Cube again. I don't really like that they don't have a lot of stuff in this section for examples that needs absolute value bars, because then you tend to forget that you have to do it. So don't forget about the absolute value bars. All right, problem 2 involves simplifying a cube root. Simplifying a cube root. Well, we've got power charts for a reason. You know, hopefully using those, looking it up, will start to click in the memory here. So absolute value symbols are not needed. Remember that to combine the nth root of a and the nth root of b by multiplication, both radical expressions must be real numbers. Well, you're not going to see any I stuff in anything that we're doing. You know, this whole chapter is supposed to be about the real applications here. So, simplifying a product. What is the simplest form of, oh my goodness. Can we multiply those together? Sure we can. Index is the same. They're both square roots. So we're going to do numbers like numbers, because numbers have different rules than variables do. So 72 times 10, hey, that's 720. No problem. But what do you do again when you want to multiply similar bases? Correct, right. How do we put x cubed and x together? We just add the exponents. So x to the 4th, y to the 5th. 3 plus 1, 4. 2 plus 3, 5. This is bigger than the last one we did. But it's square roots, so let's think through it a little bit. 720, that's huge. Huh. Perfect squares into 720. Did 9 pop into your head right away? Because of the 72? Okay, so you can kind of think your way through it. All right, if I did 9, then I'd still have 80. Is there another perfect square that's going to go nicely into 80? 4 is the obvious one, right? But now we've got a 20. Which perfect square goes into 20? Is 5 a perfect square? So what we want to know is that 9 times 4 times 4, what is that? Because that's going to be the biggest perfect square that we have that's going to go in there. What is it? Perfect square, 12 squared. So 144 goes into it how many times? You should not be shocked by that. See how this was the last number we had over there? All right, let's see here. We could do the division thing for the x's. This little 2 out here. So 2 goes into 4. Ooh, perfectly. Twice. 2 goes into 5. Well, nicely twice. With an ugly remainder of 1. So nice stuff. We got a 12 right here. Got an x squared and a y squared. Then we got some ugly stuff that's got to go in back. So 12x squared y squared, square roots of 5y. Absolute value bars? Normally, we'd say yes. I mean, we want to be looking for those odd powers, but we don't have odd powers. These came out nice and neat. Now, this one's a little confusing because I want you to look at the original. Did the person who wrote that problem really care whether or not they were going to get answers of no real solution? They didn't care. They had cubes up here. So if they had cubes up there and an x to the first up here, x or y, they could get a no real solutions. But we ended up being okay anyway because in the end, we didn't really have to check too much. We just said, hey, our powers are even down here. No baby, it's all good. Well, that was getting a little tougher. So let's do this one together. So we're going to need 45 times 35. Oops, no plus. 1575. Yeesh. X to the what? 6. Y to the what? 7th. 1575. Well, 225 would be something kind of logical with all the 5s. Ooh, cool. Square root of x to the 6th. X to the 3rd. Square root of y to the 7th. Y to the 3rd. But ugly remainder. Ugly remainder of 1. So 2 goes into 7 3 times with an ugly remainder of 1. So square root of 225. 15. How do we organize it? Pretty stuff up front, ugly stuff in the back, and last step, absolute value bars. Look at the original. Did they care? So should we care? We don't have to. They didn't care. If somebody put a negative in here, they weren't going to be able to do this. You know, it would stop them cold. Same thing here. We've got an x to the 1st. So down here, hey, that's our answer. You know. Now, will we put them on there? We'll put them on there. Because otherwise this gets really confusing for folks. So if you're thinking, okay, but then they'd write no real answer down there. I would take this with the absolute value bars. But my hope is that you would look at the original and say, they didn't care if this came out as no real answers. So why should I go to all the trouble with the absolute value bars? They didn't care. So if they don't care when we start, we shouldn't when we're done. But we do have to check for those absolute value bars. So Monday, We'll talk division. 43210 me. How do you feel about let's just do half of the objective? Multiplying radical expressions. Where do you think you're at? I know that last part kind of muddles the absolute value thing a little bit for you there because they're getting more complex. But yeah, still pretty good numbers. Excellente. Well, that seems kind of teeny. Oh, because those are all the multiply ones they have in the book. They don't have a lot of them. Oh, there we go. Oh, and you're going to notice for some of the assignments we do in Chapter 6, they're longer than what we were doing back in Chapter 5, and that's because they're much faster. You know, these are ones that we weren't spending 10 minutes on an example on any of these. So that's